Hello everyone and welcome you all in this second lecture of Back to Basics sessions where we are going to revise some more important concepts, and in this lecture we are going to see basically two topics. First one is the introduction to loads and then the design philosophies. So there are total three types of design philosophies, and we have seen that first one is the working stress method, second one is the ultimate load method, and third one is the limit state method. And basically there are three different types of loads. The first one is the dead load, second one is the imposed load, and the third one is the environmental load. Now in the previous video, if you remember, we have discussed it during the construction of a house under the structural analysis and design to estimation of the loads on the structure. So that estimation we are going to do here, all the different types of load. So we take the worst possible combination of loads, just like this is a bridge and there can be different types of vehicles moving on it. So what are the different types of load? It may be covered with snow, maybe the wind may be flowing. So these type of loads are environmental load, and you can see the dead load of the bridge as well as the moving load of the trucks. So these are the three different categories of load that may act on a structure. So now let us discuss all these three different types of load in a tabular fashion. So the dead load is of constant magnitude that remains in one position. Dead load includes the weight of the structure as well as other parts that are permanently attached to the structure. Just like we can say the beams and columns, walls, slabs, stairways, all these things are the part of the structure, so they constitute the dead load. So the imposed load are those load which can change in magnitude as well as position. So there are different types of live load, like load of people, furniture and storage, load of traffic on bridge, impact load due to vibration of moving load, longitudinal load, load due to slipping train on bridges or braking of the vehicles. So this type of load is in horizontal direction, and it also includes the soil pressure on the wall and hydrostatic pressure on dams. All these different types of load that you are seeing are caused by gravity. But the environmental loads are those loads which are caused by the environment in which structure is located. There is not a single type of environmental load which are caused by gravity. So the different types of environmental loads can be snow, wind and rain, and seismic loads or earthquake loads. Now let us come to the design philosophy. What is design philosophy? Design philosophy of a structure may be regarded as the process or the technique of selecting proper materials and proportioning of elements of the structure according to the art, engineering, science and technology. Now every philosophy is a two-tier way. The first tier is the few fundamental assumptions that we take, and the second tier is the procedure, how to proceed, how to calculate, how to design according to that design philosophy, and it reflects the way of thinking about the concepts and being that concepts into reality. So if we look at the timeline of design philosophy, in the early 1900 there was only WSM, working stress method, the most conventional and traditional method. Then comes the ultimate load method, and the modern design philosophy is the limit state method that we are now studying. So WSM method is also called modular ratio method, and I am not going to discuss it much. Let us discuss some of the drawbacks of WSM. The actual stress distribution of concrete is not described. It assumes that concrete behaves elastically, but in reality, that concrete graph is not just non-linear but also non-elastic. And we apply the same factor of safety for different types of load. 1.5. The failure mode cannot be observed. The warning before failure cannot be studied precisely. And we can't account shrinkage and creep effects by using WSM method. So seeing these drawbacks of WSM, we don't rule out this method. In fact, the IS 456 clause 18.2.2 says WSM may be used only if it is not possible to adopt the limit state method design philosophy. Alright. So now instead of discussing ultimate load method, let us come firstly to the limit state method. And this is more important to revise it. First of all, we are going to learn what is limit state design. And side by side we will also see the recommendations given for LSM in the IS 456. But before going into those recommendations, we have to understand characteristic strength and load, partial safety factor, design stress strain curve for concrete, and design stress strain curve for steel. So first of all, let us take what is limit state design. So this method is an advancement over traditional design method, which was elastic method, working stress method. But limit state method is a plastic design method because we take plasticity into account. Also, this method gives comprehensive and rational solution to design problems. And unlike WSM, which is based on calculation of working stress of material only, and the ultimate load method, which was based on the calculation of ultimate load condition only. But in the limit state method, the concept is that we do both the things. First of all is the safety at ultimate load and serviceability at working load. So we take into account of both the things, working stress and the ultimate load condition, both. And in this case, we applied multiple safety factors to different types of load for achieving adequate safety and serviceability for considering the limit state. So there are two terms here coming, multiple safety factor and the limit state. So first of all, we will take what is limit state. So we assume a hypothetical or imaginary state, and for that state we pen down the acceptable limit so that the failure do not occur and the situation remains safe and serviceable. So seeing these requirements, there are two types of limit state. The first type is the limit state of collapse or failure for the safety, and it deals with the flexure, bending, compression, shear and torsion. And the second type of limit state is limit state of serviceability, which deals with the cracks, vibrations, deflections, fire resistance, etc. So now come to the multiple safety factor, and these multiple safety factors are based on experience, tradition and engineering judgment. We do not impart on our own personal concoction. And the very basic concept of using this partial safety factor is that our design resistance of our structure must be greater than the design load effect that is going to act on the structure. So for calculating design resistance, we reduce the material strength using partial safety factor. हमने मटेरियल की शक्ति को छुपा दी and we calculate the design resistance कि इसकी शक्ति बस इतनी ही है. So we represent the partial safety factor by gamma for different materials. And for example, we use gamma C for concrete, which is equal to 1.5, and gamma S for the steel, which is equal to 1.15. And for calculation of the design load effect, we enhance the load using partial safety factor or the load factor, which is represented by gamma F. So gamma D is for the dead load, gamma L is for the live load, and gamma W can be for the wind load or the earthquake load. And we have seen clearly in the IS 456 a tabular format for getting the partial safety factor for different types of load, and adding them we get the load combination. So in one column I have kept the limit state. First one is the collapse, and then comes the serviceability, and then is the material, and then is the load. So the partial safety factor for material gamma M for the collapse is 1.5 and 1.15 for concrete and steel. For the limit state of serviceability, gamma C is same for the both material, that is value 1. And the partial safety factor for loads, that is gamma F, in case of limit state of collapse, the first load combination is dead load plus live load multiplied by 1.5. And the another load combination that is possible is dead load plus wind load or earthquake load multiplied by 1.5, or it can be written as 0.9 times dead load plus 1.5 wind load also. And the third load combination is 1.2 times dead load plus live load plus wind load. So we can always use wind load or earthquake load, but we can't use both of them simultaneously. And now the load combinations in case of limit state of serviceability is not very difficult. It is simply sum of dead load plus live load multiplied by 1, or the dead load plus wind load multiplied by 1, or it can be dead load plus 0.8 times live load plus wind load. Now in the IS code we have seen that concrete compressive strength FCK is calculated for 1 cube. But due to the structure size effect, if we see the strength of concrete in the entire structure, it is reduced by factor 0.67, that is two-thirds of the FCK. Alright, so this is the due to the influence of size on the concrete. Now this value of 0.67 FCK is treated as the characteristic compressive strength of concrete. Now we have to calculate the design strength using the partial safety factor. So the design strength of concrete is equal to 0.67 FCK by gamma C, and we know the value of gamma C is going to be 1.5, and ultimately we will get the design strength of concrete equal to 0.447 FCK or rounded to 0.45 FCK. And similarly, to calculate the design strength of a steel, we divide the yield strength of steel by the partial safety factor gamma S for the steel, and gamma S is equal to 1.15 for the steel, and the design strength of steel becomes 0.87 F by. So we have elaborately discussed also design stress strain curve for concrete, which is like a parabolic rectangular curve. So this is the characteristic curve of a cube, and the curve is parabolic till the strain 0.002, and the ultimate strain that the concrete can withstand is 0.0035 as per the IS code. So if this is the characteristic curve of cube, so we have to reduce it by the factor 0.67 to get the characteristic curve of the structure, and this characteristic curve of a structure is further reduced by the partial safety factor gamma is equal to 1.5 to get the design curve of concrete in the structure. And we have discussed in case of mild steel bar, the curve is like this, and we have a defined yield point, and we just reduce the curve by the partial safety factor gamma S is equal to 1.15, and we can easily get the corresponding yield strain also. Whereas in case of high yield strain deformed bar, there is no definite yield point for on the characteristic curve, so we adopt the method of proof stress. So that proof stress becomes the yield stress, and proof stress corresponds to the proof strain, which is equal to 0.002, and we reduce this curve again by the same factor gamma S is equal to 1.15, and we get the design strength is equal to 0.87 times the yield strength. So the elastic strain corresponding to the proof stress is calculated as 0.002 plus 0.87 F by divided by elastic modulus of a steel. So this value of elastic strain is basically used in case of design. So now comes a very important doubt that may come into your mind, is that if we compare both the design stress strain curve of concrete as well as steel, we observe that in case of concrete curve, we reduce the entire curve from the characteristic curve to the design curve, whereas in case of the curve for the steel, we reduce only the plastic curve, not the elastic curve. Why it is so? And if we would reduce the entire curve, the curve would look like this, which is not exactly correct. Why we just reduce the plastic region, not the elastic region in case of steel? Because the elastic modulus of concrete is equal to 5000 into root under FCK. So the elasticity of concrete is not constant, it varies. It depends on the characteristic compressive strength of concrete. Whereas in case of steel, elastic modulus is equal to 2 into 10 to the power 5 megapascal, which is constant. So the elastic curve in steel doesn't change even if we apply the partial safety factor. So only the plastic curve gets reduced in case of the steel curve. Alright, so this is the reason why we reduce the entire curve in case of concrete, and we just reduce the plastic curve in case of steel by the factor 1 by 1.15. Alright, so this was all for this video, and we will discuss a new topic in the next video. So till that, stay tuned and stay safe. Thank you.